Hello everybody, I'm Marco Maurizio, and despite I seem Norwegian, so I'm Italian. I'm from NTNU. My supervisor is Filippo Berto, and today I'd like to talk about corner-point singularities. So before, I would like to let you understand something with a bit of notation. So you're familiar with fracture notch mechanics, obviously. And here we have a fracture, notch tip, and the classical element with a component, with the first components. Of course, let's say we have used since we've been using for a long time, since the origins of fracture mechanics, we have used the 2D plane elasticity. For example, here we have plane stress, or we have considered plane strain conditions. But the question that could arise is, does the 2D plane elasticity work? And this may be related with the previous, be complementary with the previous talk. So, let's say not always. In fact, as I presented the last virtual conference, we have some cases where 2D plane elasticity doesn't work. In fact, here we have some experimental results. We can see how the mixed mode cases, where the assumption of plane strain doesn't work, where in fact data are not so well fitted by the 2D plane elasticity. Additionally, for example, we have the strain size effect predicted by the linear elastic fracture mechanics. It's not the experimental results are not well predicted. So, and a classical example is that of fatigue per crack. Here you can see a fatigue per crack in a classical measurement of fracture toughness. You can see here that fracture per crack has a bold crack front, but we don't know why this crack front is bold. But many researchers attempt to find the near field analytical solution of the elasticity, and the main hypothesis was that of kinematics of generalized plane strain. In fact, indeed they use this displacement field, which lead to have a constant component of stress or strain along the thickness. And however, we have that from that follows that the only stress intensity factor which depends on Z is the mod 3 stress intensity factor. Therefore, and we have a linear variation along the thickness of the specimen. So, but now we know that for crack cases, for example, we know well that here we have the normalized stress intensity factors. They varied along the crack front from the middle plane to the free surface in this way. And for mod 2 or for mod 3, here is the mod 0 is represented as the coupled mode due to 3D effects, but now this is not the moment to talk about it. Anyways, now we know that something happens near the free surfaces. And indeed, in the 70s, Bajant and Estensoro discovered what we call surface singularity. So when we have a crack front, at the intersection between the crack front and free surface, we have a point here, and this is a corner point, and I found that there is a singularity of the stress field which is different with respect to the other point inside the plate. So, and they characterized it by using spherical coordinates, the stress field and displacement field, and they saw that we have a different stress singularity, which depends on the Poisson's ratio, and an angle beta, which is the angle on the intersection of the crack front with the free surface. So, therefore here you can see better the explanation of the previous picture of both fatigue crack front. After years, so now we know that this, in case of crack fronts, we know that the crack front is shaped such that the corner point singularity is equal to the stress singularity along the crack front. So therefore we will have a critical angle such that to obtain that condition. However, let's say for brittle failure with 3 defects and therefore also 3D corner point singularities might be important for for the assessment of brittle failure. So here, to understand, we have a 3D stress state region. So in a classical crack of V notch on a plate, we know that there is a region of plane stress at a distance which approximately 2 times the plate thickness, and we know that we have a K-dominant zone and a 3D stress state region, which is the zone where the corner point singularities occur, and of course in the hypothesis of a process structured zone that is small compared to the K-dominant zone. So our goal was to understand the mechanism of so the influence of the corner point to the notch stress intensity factors, therefore the brittle failure of components. Here we have a mode 1. We consider V notch, sharp V notch, with considering cylindrical volume around the V notch. We modeled by exploiting of the symmetry. So here we have half of the plate, here the limit plane, and here the free surface. And we consider a fixed thickness, a radius equal to the half of the thickness, because after this distance we have approximately a plane stress condition. And we consider 2 V notch opening angles, a Poisson's ratio, which varies from minus 0.3 to 0.45, also to investigate what happens with the negative Poisson's ratio. So we applied an asymptotic plane stress far field in the outer periphery of the cylindrical here, in the outer periphery of the cylindrical region, assuming a unitary stress intensity factor. And so we obtain, here I'm going to show you all the results for 60 degrees of the notch opening angle. Therefore here, and with this angle we have a plane stress eigenvalue of 0.51. Therefore here we have the stress component along the bisector line, orthogonal to the bisector line. Yeah, as a function of the distance from the notch tip. Here you can see how increasing the distance from the mid-plane, approaching the free surface, we have a decreasing on the stress field. So here we have the strength of the singularity of the stress field, 1 minus lambda 1, along the thickness of the plate for different values of Poisson's ratio. So you can say how for positive, so for Poisson's ratio equals to 0, we have a constant stress singularity along the crack front, degree 1, and for positive Poisson's ratio we have, for example, 0.1, we have a behavior like this, so we have a maximum near the free surface and then a minimum on the free surface, while for negative Poisson's ratio is the opposite. So here is the result, also including a concentration near 0.5. Well, this result is in agreement with a previous result of the Matos and Nowell of the Oxford University, where they saw that near the free surface there is a boundary layer, so the region where the corner point singularity influences the stress field. Let's say that this work was for a crack. And here you can say the stress intensity factor normalized by the applied one stress intensity factor. And here we have something of interesting, like for a Poisson's ratio equal to 0, we have the same behavior before, so no effect of the corner point singularity. While for a positive, we have a decreasing near free surface. Then with the negative Poisson's ratio, we have an increasing of the notch stress intensity factor. So, in fact, here you can see the 5 element simulations. This is the strain component along Z, the thickness. Here you can see the zones of influence of the corner point. And this is due to basically the Poisson's ratio. The same if we look at the stress components. Here, for the negative Poisson's ratio, we can see that the free surface there is a higher stress field, while for positive values it's the opposite. So this is the behavior of the stress field along the crack front for 3 different values of distance from the notch tip. So we can see how it's in agreement with the behavior of the stress intensity factor. So other results, what's important for us was like to identify the strength of the corner point singularity. But to do this, however, we have problems with the stress field at the free surface, because we have numerical instabilities. You have to extrapolate the values from the integration points to the nodes. Therefore, what we did was to use the displacement. So, because the displacement obtained at the nodes of the finite model, and therefore we obtained the 2 angles at behavior, this qualitative behavior. Here we can see the work of Cook in the 1994, and for mode 1 is starting from 0, Poisson's ratio of 0. It's so qualitatively it's the same behavior, while for negative Poisson's ratio there's something different. But this was done for 2 angles of V-notch open angles, while this was for a crack. Here we have the displacements, Uy, on the free surface, L on an angle of 150 degrees, so this is the flank of the V-notch. And here you can see the logarithmic scale of how the model or the power law model of a stress field works. So now we are working on mode 3. This is still a work in progress. Anyways, consider an angle of 45 degrees and doing the same procedure I did before. So we obtain the stress intensity factor in mode 3, and we see how it decreases along the crack front, the notch front. Here we have the coupled in-plane shear stress, that is the stress induced by an anti-plane loading of plate. And you can see how increasing, approaching the free surface, the stress field increases. And this is an agreement with what's been predicted by previous researchers. So, but we tried also to load the free surface with a shear attraction to see how the component YZ, the shear component, the out of plane component, behaves, because there is a kind of famous paradox, because we have that at the free surface the outer plane shear stress component should be 0 for the boundary conditions, while we obtained by finite element modeling that we have an increasing near the Wiener-Notch tip. To understand this, we loaded the surface shear and we saw how this behavior still happens. So this is the behavior of the same component of stress on the free surface for two different thicknesses, and for no discrimination, it means that when you have every mode of loading of a notch or a crack, you have both of, let's say, you have a translation of the element near a crack, a rotation. This rotation can be described by Voltaire's discriminations, as Cook wrote in this paper. So, but no discrimination means that we constrain the rotations of the free surface, and we saw how this effect is negligible. So, because we have the same behavior of the shear stress component, therefore we are going to understand better this phenomenon. And the question is, what is the mechanism which controls the corner point singularity under antiplane loading? So this, the answer to this question is still unclear. Thanks for your attention. I hope that the Greek one is correct.